Hi everyone, welcome to number 4 in our series of basic stress analysis with ANSYS. Today we're going to be looking at the plate with a hole problem. So here we can see a standard plate with a hole. It's subjected to a load of 1000 newtons, a tensile load of 1000 newtons. The load is 0.1 meters wide, 0.1 meters high, and it has a thickness of 1 millimeter. So we can quite easily calculate the area here. As shown, and then we can calculate the force divided by area. So the nominal force is 1 by 10 to the power 7 pascals, and then we can easily find the stress concentration factor for a plate with a hole. And if you look this up on the internet or from a book of tables, you'll find that it's roughly equal to 3. So the stress above the hole in this region here, due to the presence of the hole, will be multiplied by 3. So, and the stress we should expect to see in our finite element analysis should be about 3 by 10 to the power 7 pascals. Okay, so I already have ANSYS open here, and we're going to jump straight into this and go about making a finite element model of that problem of a plate with a hole. So as usual, we start off by defining our element type. In this case, I'm going to take a two-dimensional 8-node quad element, so element number 183. Okay. In this case, we're going to assume we have plane stress behavior, and we're going to use plane stress with thickness. We're going to actually enter the thickness as a real constant here. So we'll go OK. We can close this down. We now need to define our thickness. So we go to real constants, add, and add a real constant for element type number 1, plane 183, and the thickness is 1 millimeter or 0.001 meters. So let's go OK, close. Next step as we move down the menu is the material properties. Let's use a material model for steel. So we're using the SI unit system, so we're going to use 210 e to the 9 pascals and a value of around 0.3 for Poisson's ratio. Okay, that's our material property defined. Next thing is to define the geometry. So I'm going to create an area that corresponds to the area of the plate. So let's just take a moment to go back and look at the geometry of the. Okay, so we've already entered the 1 millimeter thickness, or 0.001 meters, and the plate is 0.1 meters wide, 0.1 meters high, and subjected to a load of 1000 newtons. Okay, back to ANSYS, modeling, create, areas, rectangle by 2 corners. In this case, I'm going to create the whole rectangle just to start off with. So we probably normally wouldn't do this. We'd probably take advantage of symmetry and just create a half or a quarter of the rectangle. But just for completeness, I'm going to show you the full rectangle, and then we'll go and look at exploiting symmetry and making the model a little bit smaller. Okay, so there's our full rectangle or square. The next thing we need to do is create the circle. So create circle, solid circle. And the origin of this circle is going to be in the center of that square. So it's going to be 0.05 and 0.05 meters, and it has a radius of 0.01 meters. Okay, no it doesn't. It has a diameter of 0.01, so that's incorrect. So let's just get rid of that. So go to delete areas and below, and let's just pick the circle. It picked a square by mistake, no problem. Go up to this box, click next, OK, and then OK. We've got rid of the circle. Just do a replot just to show we still have our full square. Let's go back and do that circle again. Solid circle. This time we put in the radius, 0.005. OK, and there's the circle at the correct size. So now we need to subtract that circle from the rectangle to make the plate with the hole. So modeling, operate, booleans, subtract, areas. So if we look down here at the bottom of the screen, it says pick or enter the base areas from which to subtract. Let's pick the square, OK. Then it says pick or, OK. Once we've done that, pick the area to be subtracted. We need to pick the circle. If it doesn't pick it, just go next in this box, go OK, and OK, and there we go. So now if our plate with a hole, we need to mesh that. So maybe later on or in the next tutorial we'll talk about how to mesh this problem properly. At the moment what I'm going to do is I'm just going to mesh it with a very regular mesh. So I'm going to set the area, so in the mesh tool here I'm just going to go area set, and I'm going to pick this area and say OK. It asks me what element edge length do I want. I'm going to just say 1 millimeter. Okay, and just all the elements will then be 1 millimeter long. Go OK, and then I go back to my mesh tool and I click mesh, and this is going to give me a regular mesh of quite small elements. Okay, so that's a reasonable mesh to start with here. We could have better meshes, and we'll talk about that later on. Okay, let's just work with this for the time being. Next thing I need to do is apply my boundary conditions and loads. So I go to loads, define loads, apply structural displacement on lines. So I'm going to hold this line in the X direction. Okay, so that line is held in the X direction, and then I want to apply a tensile load to the line on the right hand side. So in order to do that, I'm going to couple the nodes on the right hand side and couple the degree of freedom together in the X direction, so they all move together as one unit in the X direction. So I go into coupling, couple degrees of freedom. I'm going to select box here. I'm going to put a box around all the nodes on the right hand side and go OK. I say I want them coupled in the X direction, and I have to give the set reference number here some number, so let's just give it 99. Okay, I can then apply my load to any one of those coupled nodes, and that load will be applied to the full set of coupled nodes. So that right hand edge will be loaded together and moved together. So let's go back into loads, apply structural force on nodes. Let's just pick one of them, doesn't really matter which. It's going to be an X direction load, and it's going to be 1000 newtons. Okay, we see the arrow has turned up there. So this error here is saying both solid model and finite element model boundary conditions have been applied to this problem. Okay, what it's saying there is that I applied a displacement boundary condition to a line here, and then I specifically applied a load to a node here. So this one is a solid model boundary condition. This is a direct application of load. It's just warning me if I was doing both in the same place, they can overwrite each other. So that doesn't apply here, so I'll just dismiss that. Okay, so if I were to solve this model now, there's nothing to actually stop that model moving up and down. Okay, we have no constraints in the Y direction. So let's just constrain one node in the Y direction just to stop it from moving around the place. That could happen due to the way the loads are transferred through the model. You can see some of these elements here aren't orientated in the along the x-axis here. Some of them are kind of up at 45 degrees, and maybe here up at 60 and up at 80 degrees. So it is quite possible we could get some internal forces causing the model to move up and down. So in order to prevent that, we'll put one extra boundary condition here. So again, apply displacement on nodes, and let's just pick the center one here, and let's just put a Y displacement on that. So that'll just prevent the model from jumping up and down and making the solution unstable. Okay, so we should be ready to solve now. Go into solution, or always remember to save your model. That all looks okay. Let's go OK and solve. Okay, solution is done. Let's go into the post processor, and let's plot the deformed shape and the deformed shape with the undeformed edge. Okay, so you can see the deformed shape is in blue and the undeformed edge behind is dashed. So as we expected, the plate has moved over, has expanded to the towards the right, and it's contracted in the vertical direction. And the hole has moved from a circle into an oblong or oval shape. So everything looks okay there. So let's go and investigate the stresses. So we want the x component of stress. Okay, stress in the x direction. Okay, so as we can see, as expected, the high stress occurs at the top of the hole, and the high stress is about 3 by 10 to the 7, or 0.3 by 10 to the 8 pascals. So let's just say our high stress is 3 by 10 to the 7 pascals. Let's go back and look at what the theory said it would be again. Okay, so if we go back and look at our theory said that the stress would be roughly 3 times what the nominal stress in the plate without the hole would be, which is 3 by 10 to the 7 pascals. So we've gotten more or less exactly the same value in our finite element analysis as our analytical theory predicted. So if we wanted to further investigate the model and see what the specific stress was at various nodes, we could list the results of the nodes. We could, zoom in a bit. But let's zoom in and query the results. So let's click on here on query results, subgrid solution, and stress in the X direction, and go OK. So now we can zoom in, and if we click on any node, we can get a specific value for that node. So you can see we're getting 0.299 e to the 8, which is basically 2.9 e to the 7 for that value there, which again is very close. And if we were to pick other nodes in the region, you can see how the stress varies. So we can look at individually each node. So again, that's quite useful if you want to look at specific nodes. Okay, so I'm going to finish that tutorial there, and in the next tutorial we're going to actually look at maybe building this model a little bit more efficiently, maybe using symmetry, maybe not building the entire model, or what we'll probably do is we'll start with this model and we'll cut bits off it and see if we still get the same result. Okay, so if you do like these tutorials, please remember to subscribe, and you can help me out a lot by clicking on some of the links and some of the adverts that pop up during the videos. Okay, thanks very much, and see you next time.